Hi, hello, and welcome. I'm Greg Jacobs. I teach at Woodbury Forest School, a boys' boarding school in Central Virginia. Last Sunday was supposed to be the Portland Thorns opening match. I am a huge fan of them and of women's soccer in general. I've always said that there are only about 2 job offers that could pry me away from teaching: the solo radio voice of the Cincinnati Reds, the baseball team I grew up with, or the radio voice of the Thorns. You see, it's important for teachers to have hobbies beyond the classroom. One of mine is, you'll be shocked, reading AP Physics exams. I've been an AP reader since 1999, and I love it. One of the pandemic-inspired holes in my soul that doesn't involve lack of sports is that the AP reading will be online only this year. Yet the rubrics will be developed and applied the same way as always. It's worth giving you some insight as to how that process happens. You see, rubrics originate with the development committee. They write a question, then they suggest how they think that the points might be awarded for that question. When the table leaders arrive for a problem, they look at this proposed rubric, but also at hundreds of actual exams. These table leaders have extensive experience with the 2 major goals of rubric development. Number 1, award credit for good physics. But number 2, don't award credit for bad physics. The table leaders discuss, argue, and refine for a couple of days. Finally, they have to present their nearly finished rubric to the rest of the table leaders, and they're a tough audience. They ask pointed questions about why the rubric reads like it does. I have to have an answer for all of them, or I have to go back with my team to the drawing board. By the time the main body of readers arrives, the table leaders have extensively probed and prodded the rubric such that we're sure it's going to work. Then it's time to train everybody to apply the rubric consistently. You see, there's no such thing as an easy reader or a hard reader. All of us evaluate the problems the same way. You see, we check. In today's show, I'm going to discuss the physics underlying last year's qualitative-quantitative translation question. That's problem 2 on the free response 2019. But I'm also going to train my pet hippopotamus, Edna, her friend Bertha, and Anthony, the mean hippopotamus, as to how to apply that rubric. I'm going to give you and my pet hippopotamus, I'm going to give you a shortened version of the training that I gave to the readers last year. So get out your own solution or look at a friend's, see how you did. Correct the parts you missed. Send any questions you have about physics or about the exam reading process to me via @JacobsPhysics on Twitter. You can even send your response to one of the parts to this question, and I'll tell you how many points I would have awarded. I'll respond to some Twitter questions toward the end of the show. For now, let's show you the first part of the problem. We're going to start one part at a time. This is the problem that I displayed last night. You can obtain this by just Googling 2019 AP Physics 1 Problem 2. So we're exploring how these masses affect the acceleration of the blocks. Block A is at rest. Block B hangs from a light string, and friction and the mass of the pulley are negligible. So the first part is, suppose the mass of block A is much greater than the mass of block B. We want to estimate the magnitude of the acceleration of the blocks after release. A lot of confusion came from the word magnitude. Translate that in your head as the amount. Estimate the amount of the acceleration of the blocks after release, and then explain your reasoning without deriving or using equations. I got a question on Twitter that said, this is from Maggie Attempts Physics. She says, they want us to estimate magnitudes of accelerations, but then they want us to explain without deriving. Are we supposed to derive in the first part, then explain in the second part? No, this is a qualitative-quantitative translation. The exam's asking you to do sort of a thought experiment. They're saying, okay, well, how would you answer this without deriving equations? How would you answer this with respect to experiment? Well, let's do the experiment real quick. I have here a string and a pulley. This is a very light object, object B, that's going to be hanging. I don't even know what that is. This is going to be the heavy object. And some people said, well, wait a second, how do I know how much more massive block A is than block B? I don't know. This is limiting case reasoning. We're asking, well, if you make this as massive as you can imagine, what would the acceleration be? Well, how much mass can I imagine here? Well, I can imagine that we've got a hippopotamus sitting here, and we've got this little space alien hanging here. Let's see what happens. Ready? I release from rest, and it barely speeds up at all. Very small acceleration, almost zero acceleration. This is limiting case reasoning. We're not asking you to calculate an actual value for that acceleration. I'm not getting out my iPad with the Bluetooth acceleration sensor. No, not at all. I'm just saying, all right, well, what does this acceleration look like? You don't have an experiment that you can do during the exam. You have to do the thought experiment. And in that thought experiment, I've come up with, hey, that's a small acceleration, close to zero. So how do we grade this? Well, when we made the rubric, we started with 1 point for the answer. I'm not going to give you the official rubric here. If you want that official rubric, you can Google it. You can find the solutions or the scoring guidelines for this problem. I'm going to give you the condensed version so that I can train Bertha, Edna, and Anthony. So, condensed version. Part 1, 1 point for the correct answer, that is something close to 0 meters per second. Nearly zero, small acceleration, and words of justification. And those words, and a second point, do not confuse velocity and acceleration. 1 point for the answer with any kind of reasonable justification, even if it's only partially correct. And the second point is if that justification simply does not confuse velocity and acceleration. Well, how do I know how to apply that rubric? I mean, there's a million possible answers. There's 200,000 possible answers because that's how many people take this exam. All right, well, let's look at some samples. Let's look at some actual student responses. We're going to pretend for now that my pet hippopotamus, Edna, her friend Bertha, and Anthony, I'm gonna let you see these folks up close. This is Bertha. This is Bertha here. This is Edna the hippopotamus. And this is Anthony, who Edna thinks is a mean hippopotamus. And they are going to learn how to grade the exam. They're going to look at student samples and figure it out. So Edna, you're going to look at this sample here. Please read it briefly. I will read it to you in a moment. Edna is reading. The A equals 0. Because the force will be very small since it comes from B pulling down relative to the very large mass of block A. So small force, large mass means near zero acceleration, like hanging a feather attached to a big steel block. Wow, that's almost like my idea of hanging a alien that's very light by an hippopotamus. All right, does this get credit? 1 point is for the answer and words of justification. That is not mathematics, but words. Yep, they get the first point. And the second point, do they confuse velocity and acceleration? Nope. So they get 2 points for this part. It really is that simple. All right. Bertha, what does your paper say? The magnitude of acceleration would be near 0 meters per second squared. That gets the first point. It's right. There are words. Okay, let's read the words. Imagine a human pulling a mountain with a rope. The mass of block A is so much greater that the weight of block B is not sufficient enough to make a movement. No movement is no change in velocity, is no acceleration. All we need to know is, did they confuse acceleration and velocity? They did not. Acceleration is the change in velocity, so this person has given us a beautiful answer. 2 points. At the exam, at the reading, we don't actually write on the tests. Just so you know, we have to grade without writing a thing. No comments, no words, no nothing. All right, Anthony, here's your chance. The paper that Anthony's reading says, block B will accelerate to the floor at an acceleration of mass of block B times gravity, mBg. This is because the, whoa, Anthony, stop reading, stop reading. Because in this case, the answer has to be right. We have to have a reasonably correct answer here in order to continue reading to get the second point. That's not universally true for every AP problem we do. But if in this particular problem, if the first part is wrong, we don't continue reading for the second part. He's got the acceleration being mg. That's not even an acceleration. So we just don't bother to read the rest. No points. All right. Thank you, Anthony. Let's move on to part B. I told you, or part A2, I'm sorry. If you want me to look at yours, feel free to tweet it at me at Jacobs Physics, as you see behind me. Now, suppose the mass of block B is much less than the mass, or block A is much less than the mass of block B. And again, we want to find the magnitude of the acceleration. What are we doing here? That means instead of a space alien hanging down here, we're going to have something heavy hanging down there. And instead of something light hanging down there, we're going to have something heavy. So I'm going to reverse this. So my little space alien is here. I'm going to take this 1 kilogram object and I'm going to hang it here. Now I know you can't see this 1 kilogram object, but I want you to imagine what it's going to do. All right, you ready? I can't even hold this. You ready? Set. I'm going to release this and watch the acceleration of this guy. Watch how much it speeds up. Let's think what just happened to this. This 1 kilogram object, the heavy thing, might as well have been in free fall, because this thing is so light, the tension in that rope was so small that this thing might as well have been in free fall, close to it. What's the acceleration in free fall? G, 10 meters per second per second. So the answer is the acceleration is close to G, or just G would be fine. Now let's look at some samples. Again, you can't do the experiment on the exam, but you can do the thought experiment. That's what we're doing every time. All right, Edna, what does yours say? This did not switch. There we go. This person says acceleration is equal to G. Remember, this one is only, oh, I didn't tell you how to grade this one. I got to show you how to get the point here. This is only 1 point for part A2. For both the correct answer with words and not confusing velocity and acceleration. Just 1 point for the whole thing. So let's read this one, Edna, and tell us, does this get the point or not? Acceleration is about G. That's correct. Since assuming mass B is bigger than A, the system can be treated as block A free falling since it's frictionless, in which case it accelerates at G. That is correct. So, Bertha, what do you think of this one? The acceleration will be fairly large. The force of block B will be large compared to block A. Therefore, this will also cause acceleration. The blocks need to be large due to the mass difference. Less force needs to move a smaller mass. Well, what do you think of this acceleration will be fairly large? What is large? Is 10 meters per second large? Well, yeah, but is that large compared to 20 meters per second, compared to 30 meters per second? Large can be as large as you want. This person did not give us the right answer. The right answer is the acceleration approaches the free fall acceleration, approaches G. So that's not a correct answer, whatever they said here. So no. Now you say, wait a second, I thought in part A1 you said I could say it's a small acceleration. Well, what's the smallest acceleration you can think of? Think about it. Answer is 0. So as small as you can get is 0, which is the right answer. Here, the largest acceleration you can think of is way bigger than the correct answer. So this does not get the point. And finally, for this one, what does Anthony, the mean hippopotamus, have? See, I don't think Bertha thinks Anthony is as mean as Edna thinks he is, but close to 10 meters per second, that's correct. Since block B is nearly in free fall, it will fall at the speed of gravity. Well, that's wait a second. Does gravity have a speed? No, there's an acceleration in free fall due to gravity, but there's no such thing as the speed of gravity. This is what we mean by confusing acceleration and velocity. The answer is right, but this person confused speed and acceleration, so that is wrong. All right, let's move on to part C, or to part B. Part B wants a free body diagram. Forget about whether the masses are bigger or smaller than each other. We just want a free body diagram. When we draw a free body diagram on the AP exam, we need to start the diagram on the dot, start all arrows on the dot, and draw arrows away from the dot. It tells you that. Block A has a weight. Block B also has a weight. We always start there. What else is touching block A? Well, the table is touching block A. We call that the force of the table on the block, or Fn. What else is touching block A? The rope. The rope provides a tension. What else is touching block A? Nothing. So no other forces. What about block B? What besides the earth is pulling on block B? What is touching block B? The rope. What else is touching block B? Nothing. That's your full free body diagram. How do we grade this? Well, we gave this 3 points. 1 point for the normal force on block A. 1 point for the gravitational forces on both blocks, and no extraneous forces. No extraneous forces means no normal force on block B, no force of the, no additional force of motion or something like that. And then the tension force is correct on both blocks. That is to the right on block A and upward on block B. Let's see if we can look at a few solutions. Here's Edna's solution, or not her solution, but the one she's grading. Edna looks, and this person wrote out in words, not just Fn, but normal force, not just T, but tension. All right, but we still apply the rubric the way it's written. I understand all this. Do they have the normal force on block A? Check. Do they have the weight of both blocks? Check. So that's the second point. They only get one of those. And then, do they have the tensions? Correct, 3 points. Bertha, what do you think of that free body diagram? Do they have the normal force on block A? They crossed it out. So what do you think we do, Bertha? The answer is we don't read crossed out work. We ask you on the exam not to bother to erase. Just cross something out if you want to get rid of it. That saves you time. But once you cross it out, I imagine it's not even there. Now, what if you crossed it out and said, oh, wait, I didn't mean to cross that out? Well, you could have written down, oh, wait, reader, I mean that. That's okay. Read it. This person didn't do that. They crossed out these forces. Therefore, Bertha, you cannot give credit for Fn. They didn't think it was there. Do they give the weights of both blocks? Nope, they crossed that one out too. So no credit for the first one, nothing for the second one. Do they have the tensions correct? Yes, they do. So they get 1 out of 3 for this one. We cannot interpret what we think you mean. If there are 2 possible answers, we have to choose the one that's wrong, because you're not allowed to say, well, it could be this or it could be that. No, that's like a pitcher pitching and I'm the umpire and say, well, it could be a strike. Well, yeah, it could, but it's not. It's a ball. One more. This one is Anthony. Anthony, what do you think of this one? Do they have the normal force on block A? They do. Do they have the weights? Yes. They didn't say mg, they said w. You might have used fg in your class. You might say F sub e for the force of the earth. You might have written out force of the earth on the object. That's fine too. Full credit for the second point. What about the third point? Do they have the tension forces? No, Anthony, they don't. It says F applied. What does that mean? We're very loosey-goosey about labels on diagrams. If we can in any way say, yeah, they mean the force of a rope on an object, FR, FT, T, rope, anything like that would work. But F applied, that doesn't mean anything. All forces are applied. Yes, I know there is a bad physics textbook out there that uses applied force all the time. That's still wrong. F applied doesn't count. We need some indication that that's the force of a rope. So this person gets 2. Thank you, Anthony. Good job. All right, that's still just a free body diagram. Let's do something interesting. We are ready to derive in part C. Derive the equation for the acceleration of the blocks. All right, interestingly, I'm not going to spend a lot of time on this because I did this exact problem when I did the two-body show about 2 weeks ago. Look at the show that talks about two-body problems. There's 2 ways to do this. You can use the whole system and say net force equals m system times A. Plug in for the net force. The net force is the weight of block B, because that's the only thing that's it's the only external force that's pulling the system. Mass of the system is this. And then we solve for A. That's one way to do it. The other way to do it is to consider each block separately. The free body diagram for A in the direction of acceleration is T minus 0 equals ma, or that's the mass of A. For block B, we start in the direction of acceleration, which is down, and say mbg minus T equals mba. Then we stack these two equations and add them together. T minus T equals 0. mbg ends up on the left. maa plus mba. I'm going very quickly here because I did this for you in that show about two-body problems. Please go look at that if you're at all confused. You end up getting the same thing. When you solve for A, factor out an A, you get the same thing. So how do we award the points here? There's two possible ways to do this. If you did the two separate free body diagram approach, then you get 1 point for writing the separate equations for each block. As long as I can identify that you are writing two separate equations for two free body diagrams, you get that point. 1 point for combining the equations, like I did, and then 1 point for the correct final expression. But you didn't have to do it that way. When the table leaders arrived, we recognized that there are two legitimate approaches here. So we figured out how to award credit consistently, no matter which approach you took. For the system approach, we gave you 1 point just for writing that whole system equation without a tension variable, 1 point for substituting the correct values for net force and system mass, and then 1 point for the correct final expression. So let's grade a couple of these with this. Feel free to take a screenshot. This is all available in more complicated form by just Googling on the College Board sites. So here is one problem. This is the one that Edna is going to grade. Which approach did this person use, Edna? They used the whole system approach. I can recognize that because they have the word system in there. It's very clear that this applies to the system, so 1 point. Did they do the second part of the system approach, which means substituting net force and system mass with correct notation? The net force is, that's not the net force. That's not the net force there. That is that's something different. The net force is just mbg. ma plus mb is the system mass, but they did not substitute the correct system net force, so they don't get that point. Did they get the correct answer? No. So 1 point out of 3. Okay, good job, Edna. All right, Bertha, you get somebody who used the two-body approach, the two-object approach. Let's see if this person did it. Did they use the system or the two free body diagram approaches? They used the two equation approach. They've clearly marked B and A, and they've written correct equations. They don't even have to write correct equations for that first point. They just have to identify that they are using two separate Newton's second law equations, and they do. So 1 point. Did they combine the equations with correct notation canceling the tensions? Yes, they did. They told me they factored the A out. That wasn't necessary, but they communicated nicely by writing that, so I know what they intended to do. And did they get the correct expression? Yes, they did. So, hey, Bertha, you get to give a 3. Very nice. And Anthony, you get to evaluate this one. Well, here's one place where I absolutely agree with the look on Anthony's face. The problem says derive. The word derive, I mean, they have a fancy definition of that on collegeboard.com. I'm telling you what my definition of derive is. My definition is communicate using mathematics. Did this person communicate using mathematics their solution to the problem? No. They just got an answer. Is the answer right? Yeah, but who cares? That doesn't cut it. Imagine that your English teacher asked you to write a 3-page paper with textual references looking into the relationship between Romeo and Juliet. And imagine you turned in a 3-word essay that said, he loved her. What's your English teacher going to give you? He's going to give you this. And you're going to deserve it. And how do you think the English teacher is going to react when you go in and say, but English teacher, my answer's right. He did love her. That doesn't matter. That's not how to do this. Derive means communicate through mathematics. You didn't do that. You get 0 points. Not even the answer point? No, the answer point requires supporting evidence. So nothing, nothing, nothing. Love the expression, Anthony. You are correct. All right, now we get into the heart of qualitative quantitative translation. This is the most important part of the problem. It's only worth 1 point, as a matter of fact. But every quantitative qualitative translation is going to ask you to compare mathematical reasoning to experimental reasoning. We've already done the experimental reasoning in part A. Now is our chance to do the mathematical reasoning. I'll do it right to start with, show you how I would do it. Here's our expression either way. The question is, when block A is much less in mass than block B, so A's mass is small, the question is, does this equation agree with our answer in part A2? Well, let's start with, what does this equation say when mass A is small? Let's just plug in 0 for mass A. Well, that's what the mathematics says. If I plug in 0 for mass A, or something very small, you want to plug in like a 1,000th of a kilogram and let mass B be 1,000 kilograms, sure, you're going to get the same answer, something very close to G. So now I have to check, and did I say that in part A2? Well, if I said the acceleration is G in part A2, then I would check the box that says yes, and I would get full credit. But let's say that I got part A2 wrong and I had said the acceleration is enormous or 0 or something wrong. Well, then I could still get credit by saying no and then explaining that the mathematics says G, and I said experimentally the answer was not G, so these don't match. Notice that explain means I need to use words. So down here, I'm not doing this fully out because I need to explain now that this is what the mathematics says, and I have to compare this in a sentence or so to what I said in part A2. So let's look at a couple of these. It's only 1 point for doing it right. Here's someone who got the right answer in the right expression in part C, and who had the right result in part A2. Don't even look at the checkbox, just read. Since mass of A is way smaller than mass of B, this becomes just MB, the equation becomes this. That's the same thing I did. Also, limit becomes G. Wait, limit, that's calculus notation. This isn't a calculus exam. Well, it's not. You don't have any reason to be using calculus notation or principles. That said, all of your readers are fluent in calculus. If you're sure you're right, feel free. We can understand this. I know what that means. It means the limit is this, as MA becomes 0 is G, and that's correct. And that's what they said before. So Edna says, give him a check. Here's another qualitative quantitative translation. This one is for Edna to take a look at. This person did kind of what I said before. What did they plug in? MA plus MB, they're plugging in MA being like 0.01 kilograms and MB is 9,000 grams or something like that. All right, so they do the math and they find that this is just basically G is the acceleration. That's mathematics. They have to have both mathematics and experimental reasoning. As you can see from the work, if MA is incredibly small, it gives you this, which is equal to 1G. The equation pretty much becomes this. That's words, that's a subject and a verb, and that's what they checked in the first part, so they get the point. And finally, this was their solution to part C. Anthony doesn't like that solution to part C because it's wrong. But we're still going to read on. The qualitative quantitative translation says, let's see what we got here. With this equation, if block A is less than the number that MB and G is divided by less, that means the acceleration will be equal to the tension force of block B on the string. What? That doesn't say that. So no, Anthony, that's ridiculous. Your expression says it all still. I bring this up here, though, because this student could have gotten some credit here with this wrong answer. What if they told me, hey, when MA is small, then the acceleration gets very big here because the denominator being small makes the whole fraction large. Okay, then they look back at part C and they said, well, wait, in part A2, they said the acceleration should be G, but the mathematics says that the acceleration should be enormous, like infinite. So no, they don't match. Well, then we would have given them credit for being consistent there. Or if they had said in part A2, the acceleration will be enormous, and they said, well, that's because MA goes down, the denominator small makes the numerator big, and they said yes, then we would have given them credit. The point here is for relating the mathematics to the physics while doing it correctly. Even if the entire thing isn't correct, if that process is done correctly, you're going to get the point for the qualitative quantitative translation. All right, we have time for one last part to this problem. Good thing, because there is one last part to this problem. It's part E. You might as well have said, we didn't, but we might as well have said from the rubric that part E is 0 points because very few people got this. But how do we grade it for the people who did get it? The question is, what happens if we use a second pulley with non-negligible mass? If we use a second pulley, like my red pulley here, with serious mass? You remember I did this in the two-body problem show. I put this on and we see what happens. Well, the answer is the acceleration gets smaller when we put a massive pulley on there. Why is that? Let's look at the whole system approach. If we use a whole system approach, the net force, even with a massive pulley, is still mb times g. But now there's more mass that has to speed up. There's the mass of A, there's the mass of B, and has to do with the mass of the pulley, but it's really the rotational inertia of the pulley. It gets complicated, but know that there's just more mass that needs to speed up. So the acceleration has to decrease. You could also get to that through energy, since we're losing the same amount of potential energy from the system. The mass B is dropping the same distance. Then we are converting that potential energy both to linear and rotational kinetic energy now, because there is a rotational inertia for that pulley. Therefore, there's less kinetic energy that goes, or there's less energy available for translational kinetic energy, and the thing will speed up less. That's what acceleration means. It doesn't matter. The question says, briefly explain. We don't have time to go through any of these long discussions. We don't even have time to go through the physics C derivation that is about 3 pages long, that draws 3 different free body diagrams and uses Newton's second law both for rotation and linearly. Who cares? The acceleration is smaller. That's a subject and a verb. Then, since the acceleration decreases, let's look at the free body diagram of block B. We've got mbg and we've got tension. How are those balanced or unbalanced? Well, in the first situation, there's acceleration. So these guys are unbalanced. And the acceleration is down, so I'm going to exaggerate. The forces are unbalanced. In the second situation, the acceleration decreases. That means the net force, the difference between the down and the up forces, is less. The forces are less unbalanced. The forces are closer to balanced. Since mbg can't change, that's the force of gravity, the tension can. The tension has to be closer to mbg, still unbalanced, but closer. This was T1, this is T2. You can see from my diagram, since the forces have to be closer to balanced in the second situation to decrease the acceleration, the second tension has to be bigger than the first tension. And that's the answer. That's a complicated problem. If you don't thoroughly understand that, you're still going to get 10 out of 12 points. Let's show you the rubric. It's very simple, 2 points. 1 point for saying the acceleration becomes smaller. Doesn't matter why you get there, but 1 point for that. And then 1 point for a consistent checkbox. Smaller acceleration means T2 is greater than T1, like I showed you. But I'm going to show you that it's possible to get a consistent checkbox and get that second point, even if you don't get the first point right. We'll show you that. Edna, grade this one for me, please. Put Edna out while you read. Since the pulley has mass, energy will be used to rotate it. Yeah, so what? Therefore, less energy will go into accelerating the system. Who cares? So the acceleration will be smaller. In this problem, we are just looking for that. You don't know that ahead of time. You can't guess at what we're trying to ask for here. All you can do is answer the question. In this case, though, as a reader, we just look to see, hey, wait, did they say acceleration will be smaller? They did, 1 point. Now, once they say acceleration is smaller, doesn't matter how they get there, do they conclude that T2 is greater than T1? They do. Edna, give them 2 points. All right, Bertha, your turn. You're tempted to look at the question here, say, oops, they got it wrong. You can't do that. In this problem, you have to read the whole thing. Start by reading to see what did they say about acceleration. Blah, 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 blah. If acceleration decreases, they got that point. Acceleration decreases. So 1 point for that. Did they use that to conclude that T2 is bigger than T1? They did not. So they get 1 out of 2. All right, Anthony. Anthony, you're going to have to wipe the scowl off your face for now, because this person is going to get more credit than you think. Like I taught him, Anthony read, while acceleration has stayed constant. That person comes to the wrong conclusion about acceleration, so it does not get the point. But don't stop reading, Anthony. Now we have to look at what box they checked. The acceleration stays constant. They could have checked box 2 here. If the acceleration doesn't change, then the tension can't change either. So if this person had concluded that T2 is equal to T1, they could have had the second point. Turns out they checked the wrong box that is not consistent with their statement. But wait, didn't they check the correct box? Doesn't matter. In this problem, we first look for what they said was going to happen to the acceleration. This person said acceleration stayed constant. So in order to get the second point, they have to tell me the consistent conclusion about the tension, which would be this. So this person gets 0. Folks, don't game the test. Don't try to say, well, I wonder what they're going to want me to say. You had no idea what this rubric was when you approached the test to begin with. All you can do is answer the problem using the physics principles you understand. Communicate with the readers. Since the problem says briefly explain, you know that we are not asking for 10 different paragraph points. All we're asking for is for you to explain what you can understand in 1 sentence. 1 sentence could be acceleration decreases, therefore the forces must be less unbalanced. T2 is greater than T1. That's good enough. All right. Can I do this problem experimentally? I probably could. And I mentioned that because one of the most frequently asked questions that I have, I mean, I know it, not just probably, I did it. I mean, I hold this here. If you really want to go to extremes, I have this rotating platform, and I could put this over here and put the string over top of there, and you can see that the acceleration decreases. I'm asked a lot, are there going to be experimental questions on this year's AP exam? Because it says no, but you keep talking about experiments. Folks, there is no question that is exclusively devoted to experimental design. Yet we need to understand experiment, because the heart of qualitative-quantitative translation is do a thought experiment, show how some experiment can relate to some mathematics. The paragraph problem might well ask, hey, explain how this experiment could happen. Explain how you would test this hypothesis with an experiment. We don't know. All we know is there is not a 12-point problem that is expressly experimental design and analysis. All right, now is the time, folks, that I go to @JacobsPhysics. I know that Brad Williams is probably on there, and I've got the first one here from Pablo. He says, would you recommend over-explaining answers in free response, like blitzing an answer in Scholar's Bowl? Would you recommend providing justification using both energy and kinematics when only one will suffice, or just picking one? The answer is very clear here, Pablo. Just answer. Briefly explain means 1 sentence. Never, ever over-explain. That's the worst thing you can do. Why? Because if you over-explain and make one wrong statement, you've probably not gotten as much credit as you could have, because one wrong answer is the one we grade. Furthermore, you can't get extra credit. We're not allowed to say, oh, that's the best answer I've ever seen. I'm going to give that 13 out of 12. We're not allowed. We can only award the points that are there. That's all that matters. Somebody asked on Twitter, well, you're a reader, will you and Josh give us extra credit if we draw a picture of Edna on our exam? No, I mean, I'll love it. It'll be awesome. But drawing a picture of Edna does not allow extra credit. Nothing allows extra credit. So answer the question, stop, and move on. Great question. Thank you, Pablo. That helps. Let's see. What are the most common pitfalls students face when solving Atwood or modified Atwood problems? This is from Tarun. The most common pitfalls is combining the two approaches. Remember, we suggested, let me make sure that I'm on the full screen here. Yep, I am. We suggested that you could approach the Atwood problems, the two-body problems, either by drawing two separate free body diagrams or by drawing a single full system free body diagram. Don't combine the two. That's the most frequent wrong answer. There's also little problems of substituting the wrong mass. If you're drawing a single free body diagram for a single object, then the mass you're using is the mass of that object. But that's something that comes through practice. The big fundamental mistake is combining the two approaches, talking about the net force on the system and the mass of one object, for example. Thank you for asking that. What else we got? A says, I mean, literally A is this person's Twitter handle, says, I wrote less than G for part A1. Would that be an acceptable answer? For part A1, just less than G is not an acceptable answer because less than G could be anywhere from 0 to like 9.5 meters per second. Much less than G we accepted because much less than G means probably in the like 0 to 2 meters per second range. I don't know. We had to draw some arbitrary boundaries, but in our minds, anything less than G doesn't cut it. Definitely way less than G does. Kind of like for the second one, saying a very large acceleration, nope, that doesn't cut it. But very large near G, that's good enough. Eva says, on part C, why doesn't the whole system force get affected by tension? Why is it just MBG instead of MBG minus T? It's when we're doing the whole system approach, then tension is an internal force to the whole system. Tension is the force of the rope on each block, and that's part of the system of two objects. That's why we say the only net external force on the system is the force of the Earth on block B. The force of the Earth acts on block A too, but that's also counteracted by the normal force. The only net external force on the system is MBG. The tension is internal to the system. It pulls this way on block A and this way on block B, and we ignore that. If you're doing separate free body diagrams though, Eva, then you have to consider the tension on each of those. And I don't know how to pronounce your name, QEIS. That's a great one. You see, when I broadcast sports, I always ask, how do you pronounce your name? So I'm going to guess Cheese, but please tweet at me and tell me if I got it right or wrong. It says, why is part 2A of question 2 graded differently from part 1A if they ask for the same thing? Because we only have 12 points to give, we try not to award the same credit for the same thing, meaning we already awarded a point for separately for not confusing acceleration and velocity. So in this second one, we're just going to say, you know, it's got to be right for 1 point. There are a wide variety of reasons why a similar problem might be graded differently. There's 1,000 reasons. We got 12 points, and we have to somehow use those 12 points such that, well, you know, a student with a 9 and a student with an 8 out of 12, they might be pretty close to one another. I can't say for sure that this person did better than this one because on a given day, they might have been the other way. But if somebody gets a 10 and somebody gets a 2, the person with the 10 communicated more physics than the person with the 2. The rubrics are designed so that small differences were pretty accurate, but large differences, they're very accurate. And we have to find a way to give those points when we only have 12 of them. You can't game the rubric. There is no way, Chiefs, to know how the grades will be given, how the numbers will be given. You just have to communicate physics the best you can, and then we will apply the rubric consistently and accurately such that if you know physics, you'll do generally well. And if you don't know your physics, you won't do as well. That's all we can ask for. It's like umpiring. I mean, I am an umpire. There's a reason we do this. If my strike zone is wide, does that disadvantage or advantage a certain pitcher? Well, maybe, But overall, over the course of a season, over the course of a game, I'm advantaging both teams the same way. And it all comes out in the wash. If one person gets a strike three on the outside corner, that batter might be mad at me, but he ain't going to be so mad at me in 3 innings when I ring up the other team for the same pitch. He's going to be happy because they know what to expect. All right, there are lots more Twitter questions. I will take those. I told you, submit one of these via Twitter, and I will tell you how many points I would have given and why. Let me share with you now the problem for tomorrow. I will be with you tomorrow. This is, I need to make that smaller. This is problem 3 on last year's exam. It's about an experiment with a compressed and uncompressed spring. As I said earlier, you do need to understand how experiments work. This is unlikely to be a full 12-point problem this year, but something similar could be a 7-point paragraph problem. So let's go through this problem and its rubric from last year. I'll even do the experiment for you. Here's the second page. I will have this posted under the show notes later today. Give me 10 minutes to get some water and clear my head, and then I will be back on Twitter for another hour or so answering your questions at Jacobs Physics. That is an Ellie Carpenter jersey. She is one of my favorite Portland Thorns players, and her name is the same as my mother-in-law's maiden name, so they got me her jersey. I can't wait for the Thorns to be back. I can't wait for you all to take the exam and have a great summer where we can be outdoors and talk to one another. Until then, for my friends and my pets, Edna, Bertha, and even Anthony, this is Greg Jacobs saying, so long, everybody.